Alright, so here I have warm-up number 1, which is just doing some basic vector addition and then scalar multiplication. So when you have a number that's a scalar, we're not going over vector multiplication yet. That's something completely different. Alright, so if I'm just adding and then this -1 here, so I can just take u, which is -1, 3, and then I can actually kind of distribute this -1 through v, so I would end up with -2 comma -4. So that's basically how scalar multiplication works. You just distribute it to both the x and the y. And then now I can just kind of add corresponding parts. So -1 plus -2 is -3. 3 plus a -4 is -1, hopefully. 3 times w, same idea. I'm just going to basically multiply each part of w by 3. So I'll end up with 6 and -15. And then I think you maybe get the idea now. So for this one, just multiply 2 through u, multiply 4 through v, and then just add, or in this case, subtract corresponding parts. So I'll get -10, -10. Over here, I'll just distribute the negative into u, so I'll end up with 1 -3. And you can distribute the negative into w if you want, or just do subtraction, which is what I'm going to do. So 1 minus 2 is -1. -3 minus a -5, so that's going to be positive. Alright, so for warm-up number 2, they want us to find the magnitude of a vector, vector PQ. And it's really important the way that this is written, how the arrowhead is over the Q. That tells us that we're starting at P, so that's the tail, and that the head is at Q. And the direction is important for vectors because that's part of what they're capturing. So easiest way, I think, to find the magnitude is to actually first just find the vector itself. So we do that using the head to tail method, which basically says that we take the head and subtract it from the tail. So I would take the x values, which would be a 3 minus a -1, and then the y values, -2 minus 4. So PQ is actually the vector 4, -6 in standard position. So if I want to find its magnitude, which I'll represent as 2 lines, some books represent it with 1 line, but I think that looks a lot like absolute value, so I think that's silly. And all we basically do is a form of Pythagorean Theorem. Realistically, what we're doing is we're finding a triangle that's right here. So we're going over 4 and down -6, and that's where this vector is, and I just want to find that length. So I'm just doing a squared plus b squared equals c squared. Or in this case, a big old square root of that. Alright, so let's see. I cheated and looked at what the answer key was because I can't do math in my head sometimes. And I get that that's the magnitude, so that's how long this side length is, right there. Alright, so here we have exploration 1. And we're given a vector x comma y, and our job is to try to rewrite that x comma y, but using the direction angle and the magnitude. So just kind of a reminder for you, the direction angle is right here, starting from the positive x-axis, going counterclockwise, and the magnitude is the actual length of this side, typically represented with the double lines around it. So what we want to do is replace x and y using just this magnitude and the theta. So I'd like you to stop the video and try to figure it out yourself, see if you can. Alright, so how many of you just went right through it and didn't actually stop the video? I'm on to you, you troublemakers. If this vector, xy, is represented in standard position, then this is 0, 0, and that is the point xy, which means I can actually turn this into a big old right triangle where here are x and y, that's the hypotenuse, the magnitude, and I have this angle right here. And we can now represent x in terms of cosine theta and y in terms of sine theta, which is something that you should be somewhat familiar doing at this point, but I'll show you it regardless. So I have cosine adjacent over hypotenuse, and then sine of theta equals opposite over hypotenuse. And then if I just take each one of these and solve for x and y, I'll get that x equals the magnitude, cosine theta, and y equals the magnitude, sine theta. Okay, so x is still a cosine, y is still a sine, and now I can rewrite this and say that it's just the magnitude of the vector cosine theta, magnitude of the vector sine theta. I actually hope you can see that on the side there. And wonderful, you can. So congratulations, we can take any xy vector and we can rewrite it in terms of its magnitude and its direction. For practice 1, we're going to find the components of the vector with a direction angle of 115 and a magnitude of 6. So using what we just figured out, which is that any vector can be written as its magnitude cosine theta, magnitude sine theta, we can just use that information. So we have the magnitude is 6 and the direction angle is 115. So I can just rewrite this. And I'm technically done, but let's use our calculator in degree mode and let's actually figure out what is 6 cosine 115. So I've done that already. I got negative 2.54, and 6 sine 115, I got 5.44. And one thing I just kind of want to, point out to you, I guess, is if I were to graph this vector, I'm going to go negative in the x direction and positive in the y direction. So I'm going to be somewhere like here-ish, and that is going to be the 115 degrees. So we can do this little check to make sure that we've done it right, because this puts us in quadrant 2, a negative x value and a positive y value, and so do the direction angle. So it gives us a way of double checking our work. All right, so for practice 2, we need to find the magnitude and the direction angle. So we're working backwards, and this is going to be super important in the application style questions that we're going to get to later on. Not today, probably, but later on. So I'm given a vector u, and it is equal to 3, 2. And what I want to do is basically figure out what is its magnitude and direction angle. So one way we can do this is to just graph it and kind of visualize. And remember that if this is in standard position, that's 0, 0. So this ends up being the point 3, 2, which means I can just turn this into a big old right triangle. So I can do Pythagorean Theorem off on the side here and say that the length of u is going to equal the square root of 3 squared plus 2 squared, which is 13. And then in order to find that theta value right there, I actually can just use tangent theta equals 2/3 and then just flip it around. So tan inverse of 2/3, and that is going to be approximately 33.69 degrees. So that one wasn't that bad. Next one's going to be a little bit trickier. We got to add a slightly different step here. So I have vector v is going to equal negative 2, negative 5. Okay, so this time when I draw it, I'm actually down here. So that's going to be really important when we're dealing with the theta. It doesn't really change what's happening with our magnitude, right? So the magnitude of v is just going to be the square root of negative 2 squared plus negative 5 squared. And I don't know, that's 29 apparently. I cheated and looked at the answer key. That's basic math. So when I go to do the tan inverse of this and have, 5 over negative 2, so I'll have theta equals tan inverse of 5/2. Well, tan inverse only exists in either quadrants 1 or 2, and I know that because it's positive, it's going to give me this right here. So when I do this, what it's actually giving me is a reference angle and not the actual angle. So when I do this in the calculator, should get something like 68.2, I believe, and we need to put this in quadrant 3. So we got to think about that for a second. If this is where theta reference is, then we're just adding 180 to that value. Okay, so I'm doing plus 180, and the actual direction angle, I really hope you can see this down here, is 248.2 degrees. Ah, you can't. The worst. All right, let's try that again. Is 248.2 degrees. Apparently, you can't see that low. My bad. All right, so for exploration 2, we have this vector 3, 4, and what we want to do is shrink it so its magnitude is only 1. So if I were to just draw this, again in the standard positioning here, I would end up with, this side being 4, this side being 3, and I would have this. So its current length is equal to 5, but what I want it to be is equal to 1. So I want you to stop the video for a second, this time actually do it, and see if you can figure out how to reduce this thing so that I actually have something that's capturing the same direction, okay, but only has a length of 1 right there. All right, so did anyone figure it out? It actually has to do with similar triangles is what we can kind of use here. So if we're capturing the same direction, then we actually are just forming a little similar triangle compared to the big triangle. So I just need to find some sort of common ratio to reduce it. And I can just use the current magnitude and the magnitude I want. So I basically need to take everything and divide it by 5, and that will shrink it down. So if I have this new vector, okay, where I just divide each component by 5, this should have a length of 1. So what I'm going to do is just check, just to make sure that we're good here. So I'm going to actually find its magnitude. So I'm going to do a big old square root, 3/5 squared plus 4/5 squared. And let's see, so that's going to be 9 over 25 plus 16 over 25. 9 plus 16 is 25. So I get 25 over 25, which is 1, and the square root of 1 is 1. So this, the way that we write it is we write this big old unit and then the vector that we took. So this is the unit vector of vector v. And all we did was just take its current magnitude and we just divide each component by that magnitude. All right, so for practice number 3, we're just being asked to find the unit vector. So in order to do that, I'm just going to find its current length. Okay, so the magnitude of vector v is just going to be a squared plus b squared. So in this case, -3 squared plus 2 squared, which is going to give me the square root of 13. So I can find the unit vector by just dividing each component by the square root of 13. So I have -3 over the square root of 13 and 2 over the square root of 13. And this will be the unit vector. For example 4, we're just kind of stepping it up a notch. So we're saying, now can you find this new vector v that lies in the same direction as another vector, u, but has a length of 5. So what we'll do here is we'll kind of capture that unit vector, which is a vector that captures the direction but has a length of 1. So we're going to kind of capture that vector for u, and then we're just going to multiply it by 5. So starting off with u, which is -5, 7, I can find its magnitude by just doing the square root of 25 plus 49, so that is 74. So now I have the unit vector for vector u is going to be -5 over the square root of 74 and 7 over the square root of 74. So if I want to find this vector v, well, I know that it has the same direction as this, but its length is 5. So this thing's length is currently 1. So what if I just multiplied it by 5? I'll have the same direction, okay, because multiplying by scalars doesn't change the direction, but it will now have a length of 5 instead of 1. So I'll get -25 over the square root of 74, and then 35 over the square root of 74. Okay, so that's this new vector. So if we want to create a new vector that's in a certain direction as another vector, you just find the unit vector, which captures the direction, and then multiply by the new magnitude that you want. Practice 5 is the same as practice 4, essentially. We're trying to find vector v, which has a length of 10 in the same direction as u. So we're going to start off by just finding the unit vector for vector u. Okay, so its current length is going to be 5. So this is a 3, 4, 5 right triangle that we got here. So 3/5 and -4/5. So that's the unit vector. Vector v is just going to equal 10 times that unit vector. Okay, so I'm going to multiply by 10. And let's see here. I'm going to do it this way so I can explain how I would actually do this. So I'm going to, basically those 5s are going to cancel out with the 10 and make it just 2. So I'm going to end up with just 6 and -8. All right, last thing we got for today is this standard unit vectors. So basically, we typically represent I as the horizontal unit vector. So it's a vector that goes just in the horizontal direction and has a length of 1. And then j is the vertical unit vector. So it goes in the direction, in the vertical direction, words are hard, and it also has a length of 1. And what we can do is actually rewrite every single vector in terms of these i's and j's. And it's useful in some applications. I've used it in my programming stuff before. It's not necessarily super useful for us in this class, but you'll see that it's also not super difficult. So if I start off with this vector v, which I'm just going to say is xy, what I can do is actually separate this and say, well, this is really just the vector x comma 0 plus the vector 0 comma y. And because of how vector addition works, we would just have x plus 0 is x and 0 plus y is y. So I haven't really changed anything, even though it looks different. And then I'm going to do something similar. I'm basically going to factor out an x. Again, if I were to distribute this x back through, I would get x times 1 and then x times 0. Same thing here. All right, and this is really what I is. Okay, so that's I, and that is really j. So I end up with xi plus yj. These are the standard unit vectors, and we often will call this expressing them as a linear combination. What's kind of neat about it is it separates x and y, so we can see what just the horizontal and just the vertical components are. All right, now for the hardest examples of the day. I'm going to take this and put it in ij form, and I'm going to take this and put it in the component form, which is when you have the vector brackets. Okay, so for this, I basically just write negative 3i minus 1j. Done. And here I basically just pull the numbers in front of the i's and j's and add the vector brackets around it. Boom, done. Bye.